So in this video we'll check out problem number 6 from the 2010 BC free response set. This is a non-calculator question that involves series. And so what they give us here is they give us this function f of x defined for us up above, and then it tells us that that function has derivatives of all orders, and then they give us this new function g that's dependent on f. And then in part A here what they want us to do is they want us to write the first three non-zero terms in the general term of the series for cosine of x about x equals 0. Now this is something that if you want to use the definition of a Taylor series, you can attempt to build this from scratch, but you will be better off if you know the series that converge to cosine of x, sine of x, and e to the x. And in this case, if you know the series for cosine of x, you can quickly rattle off the first three non-zero terms and then the general term. So this is the rule that we would see within our series that converges to cosine of x based at 0. And then I just applied this rule with the index of 0, the index of 1, and the index of 2 to generate those first three non-zero terms. Now in the second part of part A, it wants us to use this, the series for cosine of x, to figure out what the first three non-zero terms and the general term for the Taylor series for f is. So what you can actually do here is you can take the series for cosine and you can replace this cosine function with that. Right? So I've replaced the cosine in the numerator of f with the series that converges to cosine. And then I have the minus 1 in the function f, and then that's over x squared. Well, what you notice here is you have a plus 1 in the series for cosine, you have a minus 1 in that numerator for f of x. So those are going to cancel. And you'll notice that every term that you're left with within this set of parentheses is going to contain an x squared. So if you factor x squared out of all of those pieces, factor x squared out of this piece, you're left with negative 1/2. Factor x squared out of this piece, you're left with x squared over 24. Factor x squared out of the first piece that's not left, so I did have to kind of rattle off another piece here, because what I recognized was, well, I lost this term when I canceled it with this, and if I need three non-zero pieces, I'm just going to have to write out the next term of the series for cosine of x and make sure I factor x squared out of it. I'm missing my exponent here. That's supposed to be an x squared in that denominator still. And once this is factored, you can cancel the common factors between the numerator and the denominator, so you're just left with what's inside the set of brackets. So what I went ahead and did after I did this cancellation, I kind of re-indexed and I said, okay, well this is my new 0 term, this is my new 1 term, this is my new k equals 2 term. I'm going to see if I can develop a general rule that would produce these for the first three values of the index. And so what I noticed was negative, positive, negative. So if the index was odd, I had a positive term, but if the index were even, like 0 and 2, I have a negative term. So I thought I could make that work that way with negative 1 to the k plus 1. So this will always be positive when you have an odd index and negative when you have an even index. I noticed that this exponent was 2 times 1, this exponent was 2 times 2, so x to the 2k will still work for the power on your x. But if you notice what's going on with these factorials, this is 2 factorial, this is actually 4 factorial, and this is 6 factorial. So we don't just have 2k factorial in the denominator anymore, we have 2k plus 2 factorial, right? 2 times 0 plus 2 gives you 2. 2 times 1 plus 2 gives you a 4, and then a factorial after it, and then 2 times 2 plus 2 gives you 6, and there's a factorial after that. So here would be the general term for that series. When we move into part B here, what they ask us to do is they ask us to try and decide if f has a relative maximum, a relative minimum, or neither at x equals 0, and then to give a reason for your answer. Now they do kind of give us a hint. They say to use the series. So normally what you would do is you'd probably take a derivative of this, you'd probably try to build your sign chart for the first derivative, and you can try to go that route to just decide if you have a relative max, a relative min, or neither. But what's kind of sneaky that you can do with the series here, here's the series that converges to the function f of x. What we can go ahead and do is we can recognize that because this series does not contain an x to the first term, the first derivative evaluated at 0 over 1 factorial times x to the first, that has to equal 0. Well, the only way that this can equal 0 is if f prime of 0 is 0. So the fact that there's no x to the first term present within this series implies that the first derivative of f evaluated at 0 is 0. If we look at this next piece here, this piece, x squared over 4 factorial, the way that the definition of a Taylor series would produce that term is you'd have the second derivative evaluated at 0 over 2 factorial times x squared within the definition of a Taylor series based at 0, producing the x squared term. Well, I've equated the definition from a Taylor series and applying the index value of 2 with the term that has the x squared in our series for f. And what I can actually do with this is I can solve it for f double prime of 0. I can go ahead and divide both sides by x squared, so basically these go away. So then I'd have f double prime of 0 over 2 factorial equals 1 over 4 factorial. So 2 factorial is 2, 4 factorial is 24. If I wanted to solve this to find the value of f double prime of x, I would just multiply by 2, and that's going to give me 2/24 or 1/12. So we know by basically equating coefficients that f double prime of x, this is a little bit wrong here, let me make the adjustment here, this is f double prime of 0, right, f double prime of 0, I should have a 0 there too, it's my fault, sorry about that, f double prime of 0 is going to be 1/12. Well, if you have at a given x a slope of the tangent line being 0, and at that same x a positive second derivative, that means that you're concave up at this location of the horizontal tangent, and by the second derivative test, if you have a horizontal tangent and you're concave up, you've got to have a local minimum at that point, and that's an application of the second derivative test. When we move on to part C here, part C wants us to begin to deal with the function g, and they want us to write the 5th degree Taylor polynomial for g about 0. And so what I went ahead and did was I realized we had this series from part A that represents f of t. So if I want a series for g of x, what I can do is I can basically take my series for f. Now I did have to swap the x's out for t's, right? We have a change of variable on this representation of f than what we dealt with in part A and B. But that's simple. I'm just swapping out the x's in the series for f with t's. And then I wanted to actually do this integral. So when I do this integral, I'm going to add 1 to the exponent here. So that's going to give me a negative 1/2 t. Same thing here, add 1 to the exponent, divide by the new exponent, add 1 to that exponent, divide by the new exponent. If you put in x in place of the t's and then you put in 0 in place of the t's and take a difference, what you end up with is you end up with this. Now the reason why I went with these 3 pieces is because I was kind of predicting what was going to happen. I needed a 5th degree Taylor polynomial. I recognized if I added 1 to this, that gave me a power of 5 on my variable, and that would generate my 5th degree Taylor polynomial. So here is that 5th degree Taylor polynomial for g of x based at 0. And so in the last piece of this, they tell us the Taylor series for g at 0 evaluated at 1 is an alternating series with individual terms that decrease in absolute value to 0. That we'll actually use to help with this explanation part, but what they really want us to do is they want to use the 3rd degree Taylor polynomial for g about 0 to estimate the value of g of 1. So g of 1 can be approximated with the 3rd degree Taylor polynomial for g evaluated at 1. So that's going to be, if we go back to part C, that's going to be the first 3 terms, right? We don't want the 5th degree polynomial, we just want these first 3 pieces here. So we're going to take those first 3 pieces and we're going to evaluate at 1, which leaves us with this. So if you do a little bit of common denominator work, you get an approximation for g of 1 of 3770 seconds. It says, explain why this estimate differs from the actual value of g of 1 by less than 1 over 6 factorial. Well, the nice thing about them providing this lead-in sentence here, they tell us it's an alternating series, and it's a convergent alternating series. So if you're trying to establish an error bound, rather than using a Lagrange error bound, you can use the error bound from a converging alternating series, which would be you are not going to be further off with this estimate than the first term that was left off of the series. And so the first term that was left off would have been, if we go back to part C one more time, the first term that's left off would have been this piece evaluated at 1. And so the alternating series error bound tells us that we're guaranteed to be within this amount. Well, this right here is going to have a larger denominator than 6 factorial, and therefore the value of this fraction is going to be smaller than the value of this fraction. So we kind of got lucky here. We didn't have to use the Lagrange error bound. We could explain why we have to be within this amount by using the alternating series error bound.